So we'll get started. Welcome to the April monthly webinar, no longer the student webinar. We're all grown up, moved to school. Anyone want to introduce themselves, make any announcements? If you're new, or if you've started doing something new and interesting, we'll let people know. Don't have Marguerite. We've got anyone from the LCAS conference committee online? I don't see anybody. But maybe just let people know that the call for abstracts has been extended, I believe, to the 24th of April. So get your abstracts in. If anyone has any questions about the conference, you can ask today. We can maybe try and answer them. If anyone wants to sponsor the conference, feel free to get in touch with anyone at LCAS, Marguerite, myself. Okay. So I think next month we will be having someone from the American Center for LCA presenting on the certification scheme that we use. But I see the Australian Packaging Covenant organisation has been doing some work around town, doing consultation on APCO targets, and I noticed in all that still this, a lot of focus on plastics, and with the focus on microplastics and litter things and not going away. And we've had a little bit of experience recently using some of the new factors. So I thought that's as good a topic as any to have a look at how the factors, are they operational? Are they ready to use? What sort of results do you get out? So feel free, anyone who's had some experience to, has anyone used the new factors that have been produced by the Marine LCA Impact Group in Canada? Yeah, cool. Then this will be new and funky for you then. Let me go through just some slides on the topic that I prepared. Let me get the right screen. Just one here. Move my calendar out of the way. Move the LCAS minutes out of the way. Note to self, always remember what's on your screen before you start presenting. So the history of litter and plastics in LCA go back a fair way. In fact, LCA really was created from a sort of litter pressure, because in 1972, when the Swiss picked up did really the second ever LCA, if you count the Coca-Cola one of 1969 as the first one. This was the second one where they were really concerned about plastics in the environment, and they then worked on it for like the next 20 years and created the whole method, because they were biodegradable polymers, sort of solved some of the litter problems, but didn't really, and they had other environmental problems. So this idea of a multi-pronged approach, to a comprehensive approach to different environmental issues along supply chains really was evolved. In 2004, RMIT were doing some work for the federal government and developed two very simple methods for litter in the environment, based on the mass of litter and its area and persistence. So one based on marine and sort of entanglement, ingestion, and the other one based on a aesthetic issue with litter. A similar method was then developed by the EU, which they actually reference the work that was done at RMIT, and in 2016, and it was based on entanglement. We'll have a bit of a look at that. And then 2018, the very clever people at the at CIRAG in Quebec, with some others in Switzerland, started this. A lot of the people who've done the work in the water domain for water impacts in LCA, started this marine impacts in LCA. And they released their factors in, I think they pre-released some before 2023, but the main ones were released in 2023. Just for those who maybe came in late, and haven't had a lot of experience of how impact assessment works, it's basically a process of, we have an emission to the environment, and to calculate an impact, we typically have a group of factors which go along the environmental mechanism. And most commonly, they might be a fate factor and an effect factor. So the fate factor is, how does the thing move about and sort of accumulate. The effect factor can be broken up. It might be broken up into a exposure factor. So how does something get exposed? What is the effect on something when it's exposed? And then what's the consequence of that effect? So sometimes that'll be maybe broken up into two. But if we translate this for global warming, we have methane being emitted. We will then have a sort of fate factor, which is like, how does the methane, how long does it sit in the atmosphere, creating the radiative effect? That's sort of its fate over time and space. How does it degrade? Those sorts of things. And that sort of gives us that sort of midpoint of radiative forcing. And then we might multiply it by an effect factor. How many people will die per kilogram of CO2 released in the atmosphere, to give us a human health consequence. And you may do other calculations for climate change based on that. So just to remember that we will talk about characterization factors. Characterization factors are usually the amalgamation of maybe the fate factor and the effect factor, just one factor that gives you the answer to get to your indicator result. Sometimes the characterization factor only gets you to a midpoint. Sometimes you have a characterization factor that gets you all the way to an endpoint. The choice between midpoints and endpoints is becoming less important these days. So before we look at the MarILCA work, just to look at what the model looked like from the European study from Bellinger et al. It just looked at entanglement, loss or harm to organisms, and marine biodiversity loss. And it did it with a very simple 0 to 1 scale for, had a fate factor. So what is the fate of how long something will persist and move into the environment? And then there was a damage factor when it's in the environment and organisms being exposed to it, how bad might it be? And we extrapolated those numbers, which were only really covered in this paper, maybe 10 materials. They only covered the materials for which they were assessing. We extrapolated that for other studies, we being life cycles, for some things. And you can see the sort of characterization factors, combined characterization factors here, where polyethylene is a 2.5, paper is 0.025, so 2 orders of magnitude smaller. Aqueous paperboard, 0.975, and so forth. So we had a little bit of resolution, but not very sophisticated. The MarILCA work, and there is, I was very tempted this week's webinar, month's webinar, could I just play the webinar that MarILCA have on their website with Anne-Marie Boulay. quality is not great, and I can't just, turn up and present someone else's webinar, but very tempting. I did have a look at it, and I suggest if anyone is really interested, go and get it from the horse's mouth rather than what my interpretation of it. But here's my interpretation of it. So it's part of GLAM, so the Global Lifecycle Assessment Impact Framework, which is being worked on for the last 10 years, but GLAM 3 is this, which we've talked about before, I think is the most recent version, and it's a globally consistent impact model. The framework which they set up in MarILCA in 2018 looks something like this. And so this is their picture of everything that they, would want to include if you had all the PhD students and time in the world. What are all the different pathways and movements and receptors and in an impact pathway for litter? And so you can see there's different sizes of plastic moving through different compartments of the environment, different things going on within compartments. And then we've got exposure pathways. How does it go from maybe being in the environment to actually affecting the receptors, people, ecosystems, physical structures? And then what's the exposure response? A plastic bag, or you swallow your credit card's worth of microplastic per year. What's the actual effect of that? And how does that lead to human health? And then similar pathways around the ecosystem quality effects. So that was the high level, all the things that they would like to look at, or basically a framework for people to work within. So the factors that have been published so far from Carella Poites et al., they've looked at one particular pathway, which is microplastics. They're not looking at they say nanoplastics that are in there, but I have a feeling from the thing maybe they're not. They're looking at them in the freshwater and marine environments, looking at the impact of those on ecosystems, and then looking at the physical effects on biota. So they're not looking at the ecotoxicity effects of substance within the plastic. Maybe the plastic has some cobalt in it or something, or some phthalates. They're not looking at the effect of phthalates on the things, just the physical effects. And when I say they're developing what those physical effects are, what does that sort of mean? What it means is that they get all the studies they can find, and I think they had 25 from their webinar. They talk about studies where they've got a potentially affected fraction of species, so damage to species against the concentration of microplastic particles in the environment. And so they then draw a effect curve. And so, there's like a no effect area where there's not much effect, and then it sort of gets steep as you get more, until you get to a point where actually everything is just killed if you've got that much microplastic in the environment. And so they had these different studies, and just to sort of, what are these things? They're mostly microorganisms. Hold on, I'm just going to put on my phone to be quiet. So they take that, so that's the effect factor bit, the sort of, what species are going to disappear when certain thresholds are met. The second part is the fate modeling. So how does plastic get to those environments and what happens along the way? And so here they talk a lot about two things that are going on. One is degradation of the polymer, and it's sedimentation. So sedimentation is largely related to the density of the polymer. So how heavy is it? While degradation is related to, if it is something which is breaking up or degrading over time, then that's a second factor which should be taken into account. And I think what what's important here is that for some substances where there is a high level of sedimentation, the actual degradation doesn't matter because the material is actually settling into sediment before it's degrading. So something like polyethylenes, high density polyethylenes, PLAs are quite dense, and so they quickly move through the environment into the sediments where they are they're out of the risk of the effect being assessed here. For other substances such as EPS, the sedimentation doesn't happen they're very light, and therefore it is really the degradation is more how they move down different size classes. So the factors that they've reduced, and this is on the bottom axis here, is the potential affected fraction of species per meter cubed per day per kilogram. So for a kilogram of stuff put into the environment, what are the affected species in a cubic meter day because this stuff exists in time. So, if you've got plastic in the environment for 1 day, that's bad. If it's there for a week, that's 7 times worse, and so forth. And you can see they've done this for about 11 different plastic fractions. And they have different shapes of plastics, and they also have different sizes. I think the sizes are represented by these different lines in the graph. And so they have sort of the heavier plastics are up here, have moved out of the environment into the sediments more quickly. Notice this bottom scale is a log scale. So these are big changes along there, and also shows pretty high levels of uncertainty as well. You're moving from 10 to the 2 to 10 to the 4 in your uncertainty values. But interestingly, like PLA, which is a degradable polymer, sits in the same band as PET and PVC. Remember, we're only looking at the physical effects here. So whether you're eating PVC or eating PET, the model doesn't really care. Polystyrene, HDPE, LDPE, they can be a bit lighter. Polypropylene and EPS has very high variability in the characterization factors. If we compare, how does that compare to other toxic things that we measure? And so this is a comparison. You can see different dots here. See the dots for, say, the EPS sitting, assume, in the light blue. Why are they moving around? Tire and road wear is way over here. And so compared to sort of aldrin, nothing's sort of that bad, and dioxin, but they are quite comparable across the thing with something like nicotine, which is quite toxic, ibuprofen, vanillin. And so the kilogram for kilogram, these are marine endpoint characterization factors. When these substances are released to the marine environment, they are similar to the factors of plastics move back and forth across some common substances that we will look at in terms of their marine ecotoxicity. Another way to compare the impacts is to look at the impact category and all the damage in a year that comes from that impact category. And so this is the measure of the relative normalized impacts for microplastics compared to all other impacts in the ecosystem quality area related to this GLAM life cycle assessment method. And what we can take out of here is that the marine microplastics 10 to the -3 PDF per year, year per year, while we have that's similar to the impacts of climate change, impacts of climate change on terrestrial species. It's 2 orders of magnitude lower than, so 100 times lower than freshwater climate change impacts, and similar to the marine climate change impacts. So if we're trading off litter versus climate, the actual species loss will be 100 times more related to climate than it is relating to microplastics. But nevertheless, microplastics are, similar to terrestrial ecotox, but yeah, tending to be on the lower side compared to many of the other things that are threatening ecological damage. So that's where it's at the moment. It's obviously it's only modeling one of the pathways, and there are many pathways. So it certainly doesn't indicate that microplastics are not important, and they're certainly within the same quanta as many other issues that we take in as importantly. So that's sort of some of the background thing. Now we get into how we actually use the factors. So we've got, the problem is, firstly, choosing an elementary flow. So the way the flows are published in the article and then reproduced in software is that you have to decide on a size fraction, a polymer type, and a shape. And so there's individual 3 different shapes, and 1, 2, 3, 4, 5 size fractions that you need to choose from. Clearly, this is not in your LCA software yet. The flows, you need to go and add them. Once you decide, okay, I now know what flow I need to add, you then need to work out how you actually work out what your emission is, because almost no one says, hey, I'm making PET cups and I'm going to put 2% of them into the ocean. So actually deciding what your litter fraction will be, if there is one, how you determine that is a real challenge. And so you might say, okay, we think maybe we lose 1% to litter, or 0.5%, or 0.5%. Very difficult. All the litter counts and things don't really help, because no one really closes the balance on for every 1,000 cups or trays or spoons you use. No one tells you how many end up in litter. They'll tell you how many they found on the beach, but they can't relate that to how many actually were used and successfully managed without litter. Having done that, you then need to work out, okay, you've lost 1% of them, but are they in the river or in the ocean? We don't have a terrestrial compartment at this point. They haven't modeled the fate compartment of how it goes from left behind on a football oval from a festival to then ending up in the freshwater environment. So you need to then make an assumption, okay, what percent does everything left in the terrestrial environment eventually end up in the river and then into the ocean? And so it's a sort of a second part of the decision making you'll need to create. There's not really a lot of guidance anywhere on how to do that fate modeling. In the examples that I'll show, we set 1% as a litter fraction. And we set it the same sort of for all litterable items. So really, whether we set it at 10 or 1% or 0.1%, the relativity between the results will look the same, because they're all being littered at the same rate. So unfortunately, the work isn't published yet. So I've had to change some names and things because this is not yet public. So but the relativities are okay. So here we've got 4 plastic carry bags made of LDPE, oxo LDPE, which is pretty much banned. So that's a pro-degradant in it, and a polybutane, a PBAT TPS, so thermoplastic starch with, this is the Martabi type polymer. It's about half fossil, half non-fossil, but it is certified compostable, both in commercial compost and in agricultural applications. And so the only difference between these two factors is actually the weight. In this, the weight of the polymer, there was a greater weight of the oxo-degradable. So they actually have the same characterization factor per unit. And for this PBAT, we have no factor, so it comes up as 0. So that's one of the limitations. Now it is a compostable polymer. I think it's quite heavy, so it would sink pretty quick also. But how well, if they're emitted directly to a marine environment, they are not necessarily well designed to degrade there. We looked at some coffee cups, and so here the plastic lined paper cup with a polystyrene lid looks pretty bad because of the polystyrene. The two other cups which didn't have any plastic, one had an aqueous lining, but that had no characterization factor. But there were polyethylene sleeves in the transport packaging of this study, and so they came up with some small amount of plastics, assuming they're equally literable over time. And then the last one looked at is a clear clamshell, which is looks at PET and PLA. And so interestingly, the PLA doesn't perform any better than the PET, essentially have almost the same value. They have different characterization factors. And I think the PLA one is slightly lower, but relative to the overall problem, the difference is not so significant. So what's next in this area? I know they're working on the impacts of microplastics in marine sediments. I actually thought those factors might be out by now. So, a whole lot of plastics being rewarded for falling out quickly and going into sediments, but we then need to work out, okay, is there an impact from being in the sediment? And so there are some fate and exposure models based on what happens with marine sediments. They have the same issue with other toxic components that fall out into sediments and how you then model those. The comparison with other toxicity and biodiversity. So I showed you that provisional stuff in GLAM. That's not complete yet. So I think there's still some work to be done to look at the relativity of this impacts of microplastics. Clearly, there are lots of other pathways, including the pathways on human health. And then I think it's more interesting, rather than having just to put in one or two factors in your foreground, which are usually, and you've then got to really, you've got to make up what your emission is going to be, because you're really very difficult to get hard data on that. So it'd be nice to have some systematic inventory of plastic leakage in the background. So what sectors and what sort of products do you use that induce plastic releases to the environment, if there are some? And I know there have been some interesting plastic mass balances done in some organizations, and they realize that once you look across all manufacturing chains and all different types of products, you can actually see that plastic leakage can come from quite a few different places, and it's very regionally specific. So that's all I wanted to sort of present as a bit of an opening. So let's open the floor for discussion and questions on the topic about whether we think this is something we should be doing more routinely. Anyone else's experiences on it?
Tim, I had a quick question. So you showed the emission, like the factors, and talked through the liter side of things. Is this model can this model also be used for like inefficient waste management systems, informal waste treatment, and leakage through poor practices and stuff like that? Is that considered litter, or is that something else?
Yeah, I think it is. I think that's what we would be interesting to look at. So in the packaging tool that we have a default that whenever you send something to recycling or landfill, there's a fraction which is littered because waste management systems just leak a bit. You know, there's a landfills leak a bit, trucks leak a bit on a windy day.
Yep.
And so as opposed to a reuse system, which will probably not leak. So we set differential leakage in there based on whether it's at an end consumer. We have less leakage when it's a material being handled through commercial waste because you've got better scale and better control of materials and things. So I think that's the work that would be interesting to do, particularly in that waste, as you say, in that waste management area. We've done a bit of work with agricultural films, and there it's tricky. If you put an oxo-degradable on an agricultural soil, you're essentially emitting the entire product to the environment. And it'll break into tiny bits of plastic, and it either stays on soil forever because it really doesn't degrade, or maybe all of it ends up in the river.
Fresh water.
Yeah.
Yeah, I guess the question is like, how do you research this, given that it's hard, it's very difficult to quantify. Like,
I think
because it's accidental.
We wait for the Swiss and the Quebec crew to just obviously they're working on it. It's a big collaborative thing, part of GLAM. So there is a strong incentive to get that improved. Just good now that the flows will be standardized, hopefully in Echo and Vent and other places, that we all know now how to document that stuff. So that could be quite valuable.
Tim, can I ask a question about something else, like the sources of the microplastics in the ocean? I think a lot of it actually from our washing machines. All the plastic we're wearing, and so how does that contribute to the analysis?
Yeah, so now we've got a model that if you're looking at alternative fabrics and fabric products, that you now could meaningfully model the impacts of those microplastics. And I know that we did a study a couple of years ago on filters on washing machines, and so obviously there's part of it is also the impact of filtering, whether you can actually intervene there. So yeah, they're all parts of the sort of foreground. How does microplastics get to the environment? Obviously, these factors, once it's there, it tells us how bad is it? Is it really bad? Is it our area of concern? How does it compare to other things? Yeah.
A question. For landfill, what's kind of like a nice default number, or do you have a default number you use for plastics leaving the landfill site as microplastics? Any kind of ballpark vibe?
Yeah, Jamie's not on here, is she? There's two answers to that. There's one, there's like the leakage, and so we've been using, I believe, 1%, which might be overkill, which is probably overkill. I think if you're consistent with across your things, you say that practice leads to this. I suppose when you're looking at different practices, probably if you haven't got a landfill collection, if you say the landfill collection is not curbside with all the things of bins being left on the street, falling over, and now we've got container deposit legislation, everyone's fossicking through the bins, bringing out cans and stuff. If it's a different thing, if it's just at the landfill, then you'd say it's probably a lot less. the amount of escape. You know, they put a fence around it. It's not huge relative to the volumes of stuff going in there. Then I would say it's probably a lot lower. The other part of it is that if you use the models that the Swiss guy, Gable Docker, who does landfill modeling for Switzerland and for, I think it goes into Echo and Vent, his models landfills for like 60,000 years or something. And so they assume every bit of plastic that doesn't degrade in the landfill will eventually be released to the environment as the landfill becomes, you know, back to being part of the environment, that those plastics will remain there, and then they are potentially a risk, in which case the volume of those plastics is huge. It's most of it. I don't know how, you know, I'm not going to deal with, if we make another couple of 100 years, then that's going to be really good. 60,000 years is just too long for me. I like a long-term approach, but it's, so I think those models are a little extreme, because then you end up with these really big spikes in impacts that are just, you know, so far in the future. Yes, is it Mario?
Yeah. Thanks, Timothy. So when it comes to stage D, how do you model the scenarios for microplastics?
For which? Sorry.
Stage D, like beyond the life cycle and scope. So there is A1 to
in
C,
module
A to C, right? Yeah,
Okay.
module D.
Yep, module D. That would only be an impact when I think the same, you know, the diff in EN 15, you're talking about EN 15804 and construction products, then it would be modeled, I think the C1 to C4, where you're managing waste, there would be emissions, potentially leakage. When you then offset virgin polymer, there is actually, I remember seeing, because obviously the recycling, circular economy, material recycling, plastics recycling does have a lot of leakage, because you're bundling plastics together, you're carting them around. But I remember seeing there is a incredible amount of leakage of resin. Like resin exists as, you know, little beads, so that flows into molding machines, and it's amazing the stats on like how much resin gets emitted to the environment, just because, you know, there's a lot of material handling. Sometimes it leaks, it's very light, blows away. There's a relative to what's used, maybe it's not so much, but it's not insignificant when you actually do one of those material flow modeling of everything, where your plastic goes and where your leakage is. That's not an insignificant leakage, it's actually leakage from just the plastics industry. And so I suppose if you are accounting for the impacts of the recycling system, will have some leakage that you can try and control and manage and measure that, then you should count the avoided leakage from the virgin plastic supply chain, which is maybe significant. That would be the only thing I think would come in. But yeah, in terms of module D, you model it like you model every other aspect of, you know, impacts beyond the system boundary.
Yeah, makes sense. Thanks.
Yeah.
Is there any modeling comparing the incineration of waste plastic compared to landfilling?
Yeah, certainly we could open up, you know, any LCA software, and you'll have those, that comparison can be done pretty easily, and is often a sensitivity in any LCA of waste management in a region where you have significant waste to energy facilities. Wouldn't affect the microplastics, because well, it does. I suppose in a way, it gets rid of the plastic, and so the microplastic fate after landfills, because landfills, I can imagine, could emit plastics for a fair amount of time. Once you burnt it, then it's gone. But the bigger problem with combustion of plastic products in incineration is that all the carbon in the plastic is fossil, and it's really released to the atmosphere. So they don't really have a greenhouse gas advantage above burning coal or any other fossil-based material. So they tend not to look very good like that, unlike biogenic material where you maybe get a slight biogenic credit. Which is curious why Victoria is going heavily down the waste to energy path. It doesn't seem to make a whole lot of sense to me. So yeah, I think those comparisons are there, but I'm not sure they have a huge effect. I'm not sure it's a solution to microplastics. Obviously, it creates particulate matter, which is way more toxic than anything in that microplastic domain from a human health point of view.
It's just very interesting that the model actually compared the impact of microplastics with climate change. You know, the government around the world, maybe not all, but a lot of the government actually taking actions against climate change. But we realize microplastics are a problem to be resolved. But yeah, I don't think the effort that we are putting in is sort of in comparison to the impacts.
Yeah, I think there's a lot of effort going into microplastics. From my point of view, it gets more effort than it's worth, but that's okay. We don't know really what it's worth. It's a big unknown, and so it's important to work out how bad it is, and deal with it. We need to deal with everything, of course. There's not one indicator versus another. So I think it's great that we are starting to get some visualization of how big those impacts are, and that the solutions are not going to be always a tension between climate change and plastics. Sometimes that's the case. In the health sector, it's probably going to be pretty hard to replace a lot of that plastic product with non-plastic product. So therefore, there could be climate consequences if we rush and overdo the shift. If we just replace everything that's plastic with something that's paper or metal, then that will have consequences. Okay. Maybe we'll leave it there. Thanks for joining today. So yeah, I think next month, hopefully, will be the American Centre for Life Cycle Assessment. They'll be staying up at night to give us a bit of a overview of what they do. In the meantime, get your abstracts in for the conference, which is going to be in Melbourne in November this year. Yeah, look